So good evening, everyone. So today we are continuing with our derivative. This session is for math. So we are continuing with our derivative. This time around we're looking at the differentiation of logarithmic and exponential functions. This one is simple also. This is an example of an exponential function. This is an example of an exponential function. This is an example of a logarithmic function. This is an example of a logarithmic function. This is an exponential. This is a logarithmic function, isn't it? So now we are going to find the first derivative of these two functions, and then we're going to look at the practical application of their first derivatives when you're looking at the nature of the graphs. So now let me start with the exponential function. With the exponential function, it's easy. If you're given y is equals to e to the power ax, we know that we can also represent this as f of x is equals to e to the power ax, right? Either way. So depending on the textbook that you're using or the demonstration that you're using, but most of the time they use y is equals to e over ax, the notation y, so that when you find the first derivative you get dy dx, right? Or you can just find f dash x if you are using this notation. So now finding the first derivative of y is equals to e to the power ax, what do? We are saying the first derivative dy dx of an exponential function like this one is going to be the derivative of the power multiplied by the function itself, right? So it's going to be the derivative of the power multiplied by the function itself, right? So which means dy dx of this function is going to be what? It's going to be e to the power ax, because the d dx of ax, the first derivative of ax, whereby a is a constant. A is a constant. Our a is a constant, right? So now we are saying, just to continue, let me try to increase the brightness so that you guys can see. Oh, I'm sorry. No, it's okay. So we are saying, to find the first derivative of an exponential function, I'm saying you're going to find the derivative of the power, right? This is the derivative of the power multiplied by the function itself. That's the first derivative of an exponential function. So this is our result. So you have to know this. When you are given y is equals to e ax, the first derivative of this dy dx is going to be what? E to the power ax. So you have to know this concept, but we're still going to do a lot of example pertaining this one so that you guys can see. So the first example 1, let's say we are given our exponential graph, which is y is equals to e to the power 2x, right? Y is equals to e to the power 2x. This is Euler's constant e, which is 2.7 something. It's just a constant. E is a constant, by the way, but you guys already know that. So we are saying with this one, so the first derivative of this exponential function is going to be what? And by the way, you guys know the nature of this function, right? The nature of an exponential function. Y is equals to e to the power ax, right? This is the nature of an exponential function, y x. This is the nature of an exponential function. So now we are finding the first derivative of this function, isn't it? whereby we are going to say, remember, the first derivative of this function, we say we are going to find the derivative of 2x, which is the power, right, multiplied by the entire function itself. So dy dx is going to be what? Dx, the first derivative of the power multiplied by the function itself, right? So now we are saying dy dx is going to be what? The first derivative of 2x is going to be what? It's going to be 2 times what? E to the power 2x, which is equals to 2e 2x. So that's it. So that's just the concept of finding the first derivative of an exponential function. But now, of course, you won't get this type of exponential. This one was easy. So what if now we have this one? Example 2. I'm just going to do 3 examples. The last one will be a little bit harder, so that, or not necessarily hard, but it's just going to contain I will try to incorporate most of the things that you have done in the past. So example 2, we are saying with example 2, you're given a function y is equals to 7 minus 2e to the power okay, let me just say e to the power 3x squared. Yes, we are given this function, right? So now we want to find the first derivative of this exponential function. We have our e to the power 3x squared, isn't it? So what do you do? Remember, how many terms do you have here? We have 2 terms, isn't it? After the equal sign, you have 2 terms, right? So remember we said derivatives can be distributive, isn't it? Whereby we have to find the first derivative of this, the first derivative of this term, right? The first term and the second term. So we know that the first derivative of a constant is what? It's 0, isn't it? So this is the first derivative of 7 is just going to be 0. And then we have to focus on this, on the second term, right? And with the second term, we have a constant of -2, isn't it? There's a constant of -2, which is multiplying e, right? It doesn't matter if we have a constant, because let me just rewrite this. Y is equals to, maybe say k e ax, right? Where k and a are constants, still we are going to get the same thing. Dy dx is going to be equals to k a e ax, right? Which means the first derivative of the power is going to multiply what? Our constant now. It was also the same thing with this case. It's just that our constant here was what? Was 1. Our constant was 1, but I didn't write the 1, right? So it's still the same thing. Which means here 1 times a, right? It's just that now our constant here, our k is greater than 1. That's it. So okay, let's do this one. Let's continue with this one. So we are saying y is equals to 7 minus 2e 3x squared, right? So dy dx is going to be what? Remember, the first derivative of a constant is what? It's 0. When you differentiate a constant, it's just 0. So this is going to be our 0, and then pardon me, and this is going to be our 0, and then our 0, and then, but you don't write this. I'm just, for those of you guys, you don't necessarily write the 0, but I'm just demonstrating. And then when you're finding the first derivative of these now, we are saying we are going to, this is a constant, -2 is a constant, right? -2 is a constant, so -2 won't be affected. -2, and then you're going to multiply by what? By the first derivative of the power, which is 3x squared, isn't it? Times by what? By the function itself. By the function itself, which is e to the power 3x squared, isn't it? So now we are going to get what? dy dx, this is dy dx, is going to be equals to 0 minus 2, which is just minus 2, times, this is times, right? Times the derivative of the power, which is 3x squared, is going to be what? It's going to be 6x, isn't it? Multiplied by the function itself, which is e to the power 3x squared. Therefore, the first derivative dy dx is going to be what? Negative 12x e to the power 3x squared. So this is it. So this is our answer. So this is pretty much about this is all what you do when it comes to logarithmic functions. But now let's say we have our last example. I just want to throw in a trigonometric function even here. So where we say now we have f of x is equals to f of x is equals to 3 over 2 e to the power 3 over 2 e to the power x minus minus e to the power sine 2x, right? So this is power f of x is equals to 3 over 2 e to the power x minus e to the power sine 2x, right? This is sine 2x. So what do we do here? It's still the same thing. Don't panic. So this is how we go about it. Okay, so this is how we go about it. So we have, after this equal sign, we have 1, 2 terms, isn't it? So we are going to find the first derivative of this term and the first derivative of the second term, right? So our first derivative, or the first derivative, which is f dash x, if we are using the notation f of x, right? Which means our first derivative is going to be f dash of x is equals to what? Is equals to, looking at this one, which is 3 over 2e to the power x. What is the first derivative of this one? It's just going, this is a constant, right, which is 3 over 2 times the first derivative of x, right? The first derivative of the power, which is x, times the function itself, e to the power x, isn't it? And then I'm just looking at the first term for now. This is just the first term, which means for the first term we are going to get what? For the first term we are going to get 3 over 2, then the first derivative of the power with respect to x. When you differentiate x, is going to be what? It's just going to be 1, right? So this is 3 over 2 times 1, right? Times 1 times the function itself, which is equals to 3 over 2ex, isn't it? That's the first term. And then with the second term now, our second term is then now, okay, with the second term we have e to the power sine 2x, right? So let me just do the entire thing. Our first term, we know that is 3 over 2ex, right? Minus, with the second term now, minus what? Minus dx of what? Of sine 2x, which is what? Which is the first derivative of the power times the function itself, isn't it? Times the function itself. So this is very simple. So we are saying with the first term is x is the first derivative of the power, which is x, times the constant 3 over 2, right? Times the function itself. So even here, it's the same thing. The derivative, the first derivative of the power, which is sine 2x, times what? times the function itself. So here, so this is what we have. So with this one, we're going to have 3 over 2 ex minus the first derivative of sine 2x. What did we say when we're differentiating trigonometric functions, whereby we said it's sine ax, whereby we have a constant within the x space. So now, first of all, we're going to find the first derivative of what is inside the sine, right, which is going to be 2, and then the first derivative of sine is going to be cos, and then we take what is inside as it is, multiply by what? By e to the power sine 2x. So that's it for this question. So okay, let me just go back a little bit. What did we do? We're given a function f of x, right, is equals to 3 over 2 e to the power x minus e to the power sine 2x, isn't it? So now we have two terms. We started by finding the first derivative of the first term, which is 3 over 2 e to the power x, right? We got what? We got 3 over 2 times e to the power x, because we had to find the first derivative of the power, which was 1, and then 1 multiplied by the constant, right, and then times by the function itself. We get this. And with this one, with the second part of the equation, the second term of the equation, our power is what? Our power is sine 2x, isn't it? So we're going to find the first derivative of the power. We're going to find the first derivative of the power, which we did here. The first derivative of the power multiplied by the function itself, isn't it? So what's the first derivative of the power? Basically, we're just finding the first derivative of sine 2x, which is something that we did last time. The derivative of sine 2x is what is going to be 2 cos 2x, which is this, right, multiplied by the function itself. So basically, this is the first derivative of this function. I'm using the exponential, the first derivative of exponential functions. So there are a lot of questions pertaining this, guys. We can also use the product rule in solving exponential, but I'm going to do that one once we have done logarithmic, because I just want to combine the two concepts and then just calculate using one equation. So now let's move on to finding the first derivative of logarithmic functions. So with logarithmic functions, it's still the same thing. Okay, it's not necessarily the same thing, but it's easy. You just have to know that. Okay, let me create my space. So if you are given a function, now we're looking at logarithmic functions. Logarithmic functions where we are given f of x is equals to ln. Okay, sorry, let me use this notation because I have to derive a general formula. So y is equals to ln f of x, right? So we have our function, which is y is equals to ln f of x. This is the same thing as y is equals to ln ax, whereby we are saying ax is a function on its own. That's why I said f of x here. So how do you find the first derivative of this type of function? This is a logarithmic function, and we know that the graph of a logarithmic function is the inverse of an exponential function. You have to know these things, especially when you're doing the applications of derivatives, whereby if you're given this is your y-axis, x-axis, we said this is the exponential graph, right? So we are going to have our line of symmetry passing through the origin. The graph of our line of symmetry is going to be y is equals to f of x, and then this is going to be, if this is our graph, this is going to be our, okay, sorry, so this is going to be our y is equals to ln ax. So they're just but my graph is not to scale, but the logarithmic function is just an inverse of the exponential function. Go look at that, and we have the what is this, our line of symmetry passing through the origin with an equation y is equals to x, right? But this is not what we're looking at right now. So now we want to prove that if we are given y is equals to ln f of x, and then we want to prove that dy dx is equals to f dash x over f of x. So this is what it means, guys. The first derivative of a logarithmic function is equals to the derivative of what is inside the logarithmic function all over what is inside the logarithmic function. So this is the basic differentiation law of logarithmic functions. So we can prove this using the chain rule. So coming back to our function, whereby we are saying y is equals to ln f of x, right? So let me say let u be equals to f of x, which means y is equals to ln u, right? Remember, okay, sometimes they will give you the logarithmic function like this, the first derivative of a logarithmic function like this, or if they said y is equals to ln x, they will say dy dx is equals to 1 over x. This and this is still the same thing. This and this is still the same thing. But we want to prove this one using this concept, but they are actually the same thing. So y is equals to ln u is the same thing as, it is actually similar to y is equals to ln x, right? So using the chain rule, we are saying, remember, first of all, we substituted f of x by u, right? And then now we have this one, right? So now we have this equation and this equation. So we're going to find the first derivative of this equation, we're going to find the first derivative of this equation, and then we are going to multiply their derivative to find the derivative of this one. So now, finding the first derivative of this equation, which is u is equals to f of x, we know that it's going to be du dx, which is equals to f dash x. That's the first derivative of this one, right? And then this is the first derivative of the first equation, and then the first derivative of the second equation is going to be dy du, because it's y with respect to u, right? Dy du is going to be equals to what? 1 over u, using this principle. So now, in order for us to find dy dx, because remember, our original function is given in terms of what? In terms of y and x, right? So we want to find dy dx. Our dy dx is going to be equals to what? It's going to be equals to dy du multiplied by du dx, which means dy du multiplied by du dx. This is the chain rule, right? And then we are saying, which means dy dx is equals to dy du is what? We know that dy du is equals to 1 over u, but we also know that u is equals to what? U is equals to f of x. So where there is u, we substitute by f of x. So coming back here, we're just going to have 1 over f of x, right, multiplied by du dx, we know our du dx here is what? Is f dash x, right? This is going to be equals to f dash x, isn't it? And then when you multiply all of this, when you simplify this, dy dx, we just get y f dash x over f of x. So this is the first derivative of a logarithmic function. So let me just write the general formula. So if we are given y is equals to ln f of x, then dy dx is going to be f dash x all over f of x. So this is what you have to know. You won't be given this. You just have to know, like, how do we differentiate logarithmic functions? How do we differentiate trigonometric functions? How do we differentiate exponential function, etc.? So these are the things that you have to know, guys. Just as I said last time, we have different functions. We differentiate them a little bit different from each other, but the concept is simple. So now let me just jump straight to an example so that you can actually understand what this is. So basically, you just have to remember this, right? So now let me make an example. Example 1. Let me find the function. If you are given, okay, before I go to, okay, this is example 1. Y is equals to ln ax plus b. This is our first derivative. We're finding the first derivative of this logarithmic function. So what I want you guys to look at, this is how you break it down. This is how you break it down. It's going to be simple. Remember, we know that if you're given a logarithmic function like this one, you know that your dy dx is just going to be f dash x, right? The first derivative of what is inside over what is inside, right? So your first step is what? Is to find f dash x, right? So you know that what is inside is what? You know that your f of x is going to be equals to what? Ax plus b. What is inside the brackets of your logarithmic function, isn't it? It's going to be what? Your f of x, right? And then your f dash x is going to be the first derivative of this function, right? But remember, when you're looking at this, a and b are what? A and b are constant. A and b are just constant. A and b are just constant. So with this one, our first derivative for this one is going to be what? It's going to be a, right? It's just going to be a. So now you have f of x, which was what was inside there. Our function, the logarithmic function, as we saw here, this is our f of x, right? So even here, this is going to be equals to f of x, isn't it? And then our first derivative of f of x is going to be a in our case here. So therefore, dy dx is equals to our f of x, our f dash x is what? It's a all over our f of x is ax plus b. So this is it. This is the first derivative of y is equals to ln ax plus b. So that's how you find your first derivative for this function. So now let me move on to another example. So just pay close attention to what I'm doing. This is actually one of the simplest concepts, really. So what if now we have they are saying y is equals to ln 2 ln 3x squared minus 1, right? We have 2 ln 3x squared minus 1. 2 is just a constant. Even here, we had the constant, which was 1, right? So it's same thing here. 2 is a constant, so don't be confused with 2. So we are just going to focus on our logarithmic function, isn't it? So what are we going to do? First of all, we have to find, because we know that for a logarithmic function, dy dx is equals to what? Is equals to f dash x, which is the first derivative of what is inside the logarithmic function all over the entire content of what is inside the logarithmic function. So our f of x is just the entire content which is inside the logarithmic function, whereby our f of x is equals to what? Is equals to 3x squared minus 1, right? So this is our f of x, is what is inside the logarithmic function. And then now we just have to find the first derivative of what is inside the logarithmic function, which is this, because we are looking for this, right? So the first derivative of this is what? The first derivative of f of 3x squared minus 1 is going to be what? It's going to be 6x, isn't it? Which means therefore for this one is just going to be the constant, you take it as it is, dy dx is going to be what? It's going to be 2, right? It's going to be 2 times this, isn't it? Our f dash x is going to be what? Our f dash x is going to be 6x, right? All over what is inside the logarithmic function, which is 3x squared minus 1. So you just simplify this. Dy dx is equals to 12x over 3x squared minus 1. So that's how you do it, guys. This is how you do it. Normally when you look at but this is still the basic thing. When you look at textbook, you'll find that if they say y is equals to k ln f of x, right? Y is equals to k is a constant, and then they will say dy dx is equals to k f dash of x all over f of x. This is what we just did here, because k is our 2 in this case, right? Our k is just our 2 in this case. So you see, we had k on our initial equation, right? And then even now we still have k after the first derivative. So our k is just a constant which multiplies the logarithmic function. So we don't pay attention to the k, we just leave it as it is, right? And then we focus on this, isn't it? So whereby we are going to find our f of x, right? And then once we find our f of x inside here, we find the first derivative of f of x, which is what? Which is going to be f dash x, isn't it? And then once we find the first derivative, we are going to divide the first derivative of what is inside the logarithmic function with the content of what is inside the logarithmic function. So our f of x is going to be 3x squared minus 1 for this function, right? Because this is our f of x, what is inside. So this is our f of x, and then we're going to differentiate this, whereby we get f dash of x, which is 6x, right? So now we have f dash of x, we have f of x, right? Then we can find dy dx, isn't it? So our dy dx is just going to be 2, which was our constant here, multiplied by what? F dash of x. Our f dash of x is what? It's 6x, as we can see here, all over what? All over our f of x, which is what? 3x squared minus 1. 3x squared minus 1. And then we simplified. So this is your final answer. So this is the concept pertaining logarithmic function. Okay, let me do another one. A third example. How many examples have we done now? I've only done 1, 2. This is example 2. Let me do a third example. Example 3, right? So with example 3, this is what we do. If we are given a function, okay, if you're given this is very, very, very powerful. Let me just, of course, I'm going to include y is equals to x squared minus ln let me say ln tan x, right? So we're given this exponential function, but it's a mixture of, this is just a mixture of a polynomial, a quadratic, and exponential function, isn't it? So we just want to find the first derivative of this one, right? So we have y is equals to x squared minus ln tan x, isn't it? So our f of x in our case is going to be tan x here, right? And also we know how to differentiate what a polynomial. In our case we have a quadratic, isn't it? So now our dy dx for this one is going to be equals to, we have 2 terms, isn't it? So we know the first derivative of x squared is what? Is 2x, isn't it? Minus the first derivative of ln tan x. This is the logarithmic part of this equation, isn't it? So with this logarithmic part of this equation, we know that our f of x is going to be what? Tan x, isn't it? And then the first derivative of our f of x is going to be what? Sec squared x. Remember, the first derivative of tan x is what? Is sec squared x. You have to remember that. So this one is going to be minus what? Minus this is going to be minus sec squared x over tan x. So this is the first derivative of this function, whereby we found the first derivative of the first term, which was 2x, minus the first derivative of this logarithmic function, whereby we said this, because remember, the first derivative of a logarithmic function is what? The first derivative of a logarithmic function is f dash x over f of x, right? F of x is just what is inside the logarithmic function, which is what we have here, tan x. And then now we have to, of course, find the derivative also of what is inside the logarithmic function, which is our sec squared x, right? But you can further simplify this, but I don't think it's necessary. You can further simplify this part of the function, right? Because we know that this is sec squared x over tan x is the same thing as sec squared x multiplied by 1 over tan x, right? Isn't it? And then we know that 1 over tan is what? Sec squared x times 1 over tan is what? 1 over tan is cos x over sine x. So sec squared x over tan x is going to be what? Sec squared is sec squared is what? It's 1 over cos squared x, isn't it? Cos sec is 1 over cos, right? Times cos x over sine x. So cos will cancel out, and therefore we are just left with 1 over cos x sine x. But you don't have to simplify it. In this case, you can just leave it in this form, unless they say further simplify this, so you can further simplify this part. So this is it about the first derivative of this function that we have. So now we have done 3 examples from both the exponential function and the trigonometric functions, and then now and of course we can apply the product and the quotient rule when you're looking at these derivatives. So now I'm going to use the product rule to find the first derivative of a graph or a function, whereby a function that includes both the exponential and the logarithmic functions. So if we are given a graph for an example, we have now I'm just applying the concept of the product rule, whereby we are given that y, let y be equals to let me just say, let y be equals to okay, yeah, let y be equals to e to the power 3x, yes, ln cos x, right? You're given this function. Find the first derivative of this function. So remember, we said if we are looking at this function, we have how many? We have within this graph itself, we have this function and this function, right? We have the exponential and the logarithmic function. So in our case, we just have something like this, dx of u v. We have two functions, u and v, right? We know that if you have two functions like this one, which means we're going to get du dx times v plus dv dx times u. So this is the formula of the product rule, right? So first of all, if you have two functions like this, you find the first derivative of one function, you leave the other, plus you find the first derivative of the function that you left here, and then you leave the one that you found the derivative of here, right? So you have u v, right? So you're going to, with this term, we found the first derivative of u, we left v, plus with this term, we found the first derivative of v, we left u. So that's the same thing that you're going to do here. This is going to power u, this is going to power v, right? Our exponential is going to power u, our logarithmic is going to power v. So how do we do it? dy dx of this function, we are going to, in this case, we're going to find the first derivative of this one, and then we're going to leave this one, right? So we're going to find the first derivative of our logarithmic of our exponential function, which is e to the power 3x, right? And then we're going to leave the logarithmic function as it is, plus here we're going to find the first derivative of our exponential function, which is cos x, and then we're going to leave what? Our exponential function, 3x. So this is it basically. Now we're applying the product rule in finding the first derivative of this function. This function contains what? Contains the exponential graph and the logarithmic graph. So now, to further work this out, so the first derivative of e to the power 3x is going to be what? Remember, this is the exponential function. So now we're differentiating an exponential function. We said what? When you're differentiating the exponential function, we find the first derivative of the power multiplied by the function itself. So, which means this is going to be what? This is going to be 3 e to the power 3x, right? So the derivative of e to the power 3x is going to be 3 times e to the power 3x, right? Multiplied by ln cos x as it is, right? Because we said we're just going to leave this as it is, plus the first derivative of ln cos x. Remember, this is a logarithmic function, which means cos x is what is our f of x. So the first derivative of our f of x, which is cos x, is going to be what? The first derivative of cos is what? It's minus sine x, right? All over, because this is a logarithmic function, guys. Remember, this is ln cos x. So the first derivative of this logarithmic function, the first derivative of this one, dx, is going to be equals to what? Minus sine x over cos x, right? Because we're going to find the first derivative of this, which is minus sine x, all over what is inside here, which is our cos x, right? So this one all over cos x, right, multiplied by e to the power 3x, isn't it? So now we just simplify this. Dy dx is equals to what? 3 e to the power 3x ln cos x minus, you can simplify this, of course. We can simplify this. Sine over cos is what? Is tan, minus e to the power 3x tan x. Because I just simplified this. We know that tan x is equals to sine x over cos x. So that's what I did here. So this is our answer. And of course here you can factor out just to further simplify, we can factor out e to the power 3x, right? Such that we are just left with 3 ln cos x minus tan x. So this is the answer for this one. So this is the last problem that I just did. These are the problems that you guys should expect on your test, exam, or whatever. These are the type of problem that they will give you. So now let me I think this one, if you just go over this one again, and then you guys will try to do it yourself and find more problems that you can do. So we're saying we're given y is equals to e to the power 3x, right, times ln cos x, isn't it? So now we are using the product rule whereby we have uv, two functions, isn't it, that are multiplying each other. That's why I'm saying it's a product that are multiplying each other, which means we're going to use this concept, right? So now what did we do? We first found the first derivative of what? Of the exponential function multiplied by the logarithmic function plus this is what we did here. This is what we did here. We found the first derivative of the exponential function multiplied by the logarithmic function, isn't it? Plus the first derivative of the logarithmic function now multiplied by the exponential function, isn't it? And then once we have found the first derivative of these two, we simplified, because we know the first derivative of e to the power 3x is what? Is 3 times e to the power 3x, isn't it? Because we said it's going to be the first derivative of the power, which is 3 multiplied by the function itself, right? That's what we got here. And then of course multiplied by the logarithmic function, because we are finding the product rule, plus here when you're finding the first derivative of the logarithmic function, this is a logarithmic function whereby you have ln cos x. So if you're finding the first derivative of a logarithmic function, what did we say? First of all, we know that the first derivative of a logarithmic function is f dash x over f of x, right? So our f dash x is what? First of all, our f of x is what? Is cos x, right? Whereby now we have f of x is equals to cos x, isn't it? And then f dash of x is equals to what? Minus sine x, right? And then of course dy dx is going to be what? F dash x over f of x if you're looking for the first derivative of a logarithmic function. And then now we have our f dash x is what? It's minus sine x, and then our f of x is what? It's just cos x. That's what we did here. That's what we did here after finding the first derivative of ln cos x. This is the first derivative of ln cos x multiplied by what? The exponential function when you're using the product rule, isn't it? So then all of these, you simplify this. We have simplified this, isn't it? And then we said sine over cos is what? Is tan, right? And then this negative is this negative, and then we have 1, 2 terms, isn't it? And then we have common we have like terms between these two terms, isn't it? Whereby we have e to the power 3x, e to the power 3x. So I just factored out that to get this expression. So this is our final answer. So this is, we just applied the product rule on an equation whereby we have the exponential and the we had the exponential and the logarithmic function. So now okay, so now we are going to, I'm just going to touch on another concept that we are going to go deeper. I think next time when we meet, I'm just going to touch like the surface of this concept, because I want us to cover a lot of ground so that you guys know what to look at when you're studying and all of that. So now I'm just going to touch on a concept that is called the implicit differentiation. Implicit differentiation. Implicit differentiation. So what do you mean when you're talking about implicit differentiation? What is an implicit function? Okay, if given y is equals to f of x, this is an explicit function. This is an explicit function because y is the subject of the function in terms of x, right? Y is the subject. That's why we are saying this is an explicit function, right? Just as y is equals to 3x squared minus 1. So y is the subject. But what if we have an equation where y is not the subject? Now that's what we call an implicit function. Implicit function, where now y is not a subject, whereby you get an equation like this: 3xy minus 4y is equals to 10. So you see now y is no longer what? The subject, isn't it? Y is not the subject of this. Y is not the subject of of this function. So in this case, what do you do? How do you find the first derivative of this one if you have a function like this one? So if you have an implicit function like this one, there's a way that we do this one. It's actually simple. With an implicit function, there are two things that we do. When we are finding the first derivative of an implicit function, we are just going to use the chain rule plus the product rule. And all of these things we have done, we have done all of these things, right? So this is how you solve an implicit function. You apply the chain rule and what? And the product rule. That's it. So the best way to explain an implicit function is just do more problems. So I will solve a couple of problems so that you guys can see what you can get the idea of what I'm talking about. But before I do that, can I just highlight one thing? If you are given let me just say y is equals to f of x, right? Isn't it? And then we know from this is the function, right? Then if you have to find the first derivative of this side and this side, of course, in terms of x, we're going to find dx of y is equals to dx of f of x, right? We're differentiating both sides. So the first derivative of y is going to be what? It's going to be dy dx, right? Times the first derivative of y is what? It's 1, which is equals to, because the first derivative of f of x is just f dash of x, right? And this is equals to dy dx is equals to f of x. I'm just proving the notation. So this is what I want you guys to look at, how we found the first derivative of y. If you're given y squared, then they say you're just given this y squared, and then they find the first derivative of y squared with respect to x, which means you're going to find dx. When they say find the first derivative of a function with respect to x, this is how you write it: dx of that function, which is y squared. What is this? Still the same thing. We are just going to we're going to differentiate this. This is the y is equals to y to the power 2, right? So the first derivative of this function is going to be 2y, isn't it? Because the power will come this side, will multiply y, isn't it? Minus 1, isn't it? So it's just going to be 2y times dy dx. So this is what I want you guys to know. Every time when you're finding the first derivative of a y function, whereby you have a y, the first derivative of a y variable or a y term, always include dy dx. Always include dy dx. If you are finding dx of if you are finding dx of 3y y cubed. This one is going to be what? Y cubed, right? So the power of y, which is 3, which is going to be 3 times the constant 3, which is what? Which is 9. We're going to minus 1 here. Y squared, right? Times dy dx always. That is what I was trying to explain here. So whenever you're finding the first derivative of a y variable, you always include what? You include dy dx, because the first derivative of y is what? It's 1 times dy dx. That's what you do. So now this is very key when you're looking at implicit differentiation. So now let me just work on an example. Example 1, looking at implicit derivatives. So example 1, if you are given a function 3x squared plus xy minus x squared, right, plus 9 is equals to 0. Let me just say is equals to 10. So how do you solve this equation? This is an implicit equation because now y is not a subject of the equation, right? And don't try to make y a subject of the equation. Don't. You'll just complicate things. Just don't. You will see, just differentiate it implicitly. So how do you do that? We have 1, 2, 3, 4, 5 terms, isn't it? So you find the first derivative of each and every term, right? But how do you do that? But first of all, you are going to show that you're going to find the first derivative of this side and the first derivative of this side, and with respect to x. So you are going to say dx of 3x squared plus xy minus y squared plus 9 is equals to dx of 10, which is a constant. That's the first step that you do. We are showing that you're going to find the derivative of this side of the equal sign and this side of the equal sign. And then now, once you have written this, then now you can find the first derivative of 3x squared plus the first derivative of xy plus the first derivative of y squared plus the first derivative of 9, which is equals to the first derivative of what? Of 10. Right, but we know that the first derivative of a constant is what? Is always 0. So let's start. The first derivative of 3x squared is what? It's going to be 6x, right? Plus, and then this is what I want you guys to look at. This is xy, right? So this is the same thing as uv. So in this term, we're going to use what? The product rule. So within an implicit function, that's why I said we use the product rule and the chain rule. This concept is the chain rule. This concept is the chain rule. And then now we have to use what's the product rule. So I'm going to differentiate what? I'm going to differentiate x and leave y. I'm leaving y, I'm differentiating x. What is x? The first derivative of x with respect to x is what? Is just 1, right? So I have y times 1 plus, and then now I'm leaving x, I'm finding the first derivative of y, which is going to be what? Dy dx times 1, right? Because every time, remember, every time when you're finding the first derivative of the y variable, dx of the y variable is just going to be dy dx times the first derivative of the y variable, which is 1, right? So this is what I did here. Minus the first derivative of y squared is going to be what? The first derivative of y squared is going to be 2y multiplied by what? Dy dx, isn't it? Plus the first derivative of 9 is what? Is 0, isn't it? Because 9 is what? Is a constant. 0, which is equals to 0 also, because we have what? The first derivative of 10, which is 0, because 10 is a constant. So if you simplify this one, you're going to get 6x plus y plus x dy dx minus 2y dx dy is equals to 0. So, okay, let me repeat this. Let me try to repeat this. So this is what we did here. If you have we had this term, we had our function 3x squared plus xy, right, minus y squared, isn't it, plus 9 is equals to 10, right? So we had 1, 2, 3, 4, 5 terms, isn't it? So this is what I said to you guys. So first of all, we're going to say dx, which means we are finding the first derivative of this side, which is 3x squared, right, plus xy minus y squared plus 9, isn't it, is equals to dx, which means we're just finding the first derivative of the constant, isn't it? So now, what did I say? We're going to find the first derivative of this term, this term, this term, and this term, right? And then simplify everything. So now let me take term by term. This is our first term, this is our second term, this is our third term, right? And of course our 9, the 9 is our fourth term, and it's a constant. So with our first term, we are finding dx of our first term, which is 3x squared, right? So the first derivative of 3x squared is going to be what? 6x, isn't it? It's just going to be 6x because we're saying the power, which is 2, multiplied by 3, which is 6, right? And then we reduce the power by 1, which is 1 here. 2 minus 1 is 1, right? So that's what we did here. It's just going to be 6x to the power 1, isn't it, using the power rule of derivatives. So now, again, we are going to what? We're going to focus on the second term. So dx of the second term of this equation, which is xy, right? And then what did I say to you? This is xy. We have two different functions, isn't it? When you are finding the first derivative of two different functions, we're going to use what? The product rule. Whereby now, first of all, you are going to leave y and then find the first derivative, multiply by the first derivative of x, which is going to be what? Which is going to be 1, isn't it? Plus, we are going to leave x, multiply by the first derivative of y, which is going to be dy dx multiplied by 1, because the first derivative of y is 1, right? And then I said whenever you find the first derivative of a y variable, is the first derivative of that y variable times dy dx, because we are using the chain rule, right? So this is the part that confuses most people, but it's simple. So simplifying this, dx is dx of xy is equals to y plus x dy dx, isn't it? And then now we are finding the first derivative. Now we are just going to find the first derivative of, remember, now we have to find our third term dx of negative y squared. This is our third term, right? So same thing here. We are finding the first derivative of a y variable. It's just going to be 2 multiplied by negative 1, which is negative 2y, and then we reduce the power by 1, which is 1, right? Multiplied by what? Dy dx. That's what you do, which means this is going to be minus 2y dy dx, isn't it? So that's how you find the first derivative of this one. That's what I did. So coming back to our original work, so we have simplified it to this point, isn't it? So now we have simplified it to this point. So now but remember, we want what? We want dy dx, right, is equals to something. We want dy dx to be equals to something. So we have what? We have 6x plus y plus x, right? dy dx minus 2y dy dx is equals to 0, right? So every term that doesn't have dy dx, you bring it to this side, such that now we're going to have x dy dx minus 2y dy dx is equals to what? Is equals to minus x, minus 6x, sorry, minus 1, isn't it? Do you guys see? Minus y. So we have y, we have x dy dx minus 2y dy dx is equals to minus 6x minus y, right? And then now we factor out the dy dx on both of these terms, right? Such that we have dy dx of x minus 2y is equals to negative 6x minus y, isn't it? Therefore, we divide this term both sides such that we make dy dx the subject of the formula, right? Which means therefore dy dx is equals to what? Negative 6x minus y all over x minus 2y. So this is the first derivative of our implicit function. This is the first derivative of our implicit function. This was our implicit function here. 3x squared plus xy minus y squared plus 9. So let me do another example for this one so that you guys can get the concept. I will do 2 more examples, and then also this is where I'm going to end today. And then also when we come back, I'm just going to start from here, and then we'll move to parametric derivatives and so on. So let's have another example. Let's have another example from here. Example 2, we're still looking at implicit derivatives. So okay, let me do a simple one again. Let me do a simple one whereby we have 3xy squared plus, oh sorry sorry guys, 3xy squared plus x squared is equals to 7, right? We have, this is our implicit function. And then now how do we do this one? Of course, dx of this side, 3xy squared plus x squared is equals to dx of 7, right? And then now our derivative is distributive. We're going to find the first derivative of this term and the first derivative of this term, isn't it? So now this is our first term, right? This is our second term. This is our first term, this is our second term, isn't it? So now I'm going to show how do you find the first derivative of our first term. We have dx of our first term, which is 3xy squared. And I assume that you guys already know what we're looking at here. We have a function of x and y, right, which is uv. We're using what's the product rule again, and we have a constant which is 3. You can just leave the 3 aside. We have a constant which is 3, right? So which means we have 3, and then I'm going to leave y squared and differentiate what's x. So I'm going to leave y squared and multiply by the first derivative of x, which is just 1, right? Plus, I'm leaving 3 outside again because it's a constant. I'm going to find the first derivative of what now? I'm going to leave x. I'm going to leave x and find the first derivative of y squared. The first derivative of y squared is going to be what? It's going to be 2y times dy dx, right? Let me write this properly. So dx of our first term, which is 3xy squared, is going to be 3y squared times 1, which is the first derivative of x, plus 3, which is our constant, x times what? x times the first derivative of y squared, which is what? Which is 2y, as we know, multiplied by what? Dy dx, because since we're using the chain rule. And I said to you guys, if this like confuses you, whenever you're finding the first derivative of a y variable, just find the first derivative of the y variable. We had y squared. The first derivative of y squared is what? Is 2y, right? Multiply by dy dx. And then you simplify this. When you simplify this, you get what? 3y squared plus 3 times x times 2y times dy dx. We're just going to have what? Here we're going to have 6xy dy dx, right? So that's the first derivative of our first term from this equation, isn't it? So then we also find the first derivative of our second term, d dx of x squared. We know the first derivative of x squared is what? Just 2x, isn't it? Using the power rule that we learned the last time. So now this is the second term, this is the first term, right? So now which means now d dx of this entire function, right? We know d dx of this entire function is what? It's 3y squared plus 6xy dy dx, right? Which is equals to the first derivative of the constant, which is 7, is going to be what? It's going to be 0. So if we want to represent, because remember we're finding the first derivative, so we have to represent this in terms of dy dx, which means we have to make dy dx the subject of the formula, which means we're going to take this term to this side, whereby you're going to be left with 6xy dy dx is equals to minus 3y squared, and then we're going to divide by 6xy both sides, so that we are left with what? With dy dx. So we're going to divide with 6xy both sides, going to divide with 6xy both sides. This will divide each other, then we are left with dy dx is equals to what? Minus 3y squared all over 6xy, which you can further simplify this to minus y over what? Minus y over 2x, isn't it? So that's our second example for the implicit derivatives. And then I'm going to do one last example, which include a trigonometric function, and then pardon me, and then that's where we're going to end it for today. So our example 3, or this was our example 2, sorry. Then now our example 3 is going to be y is equals to let me just take a simple function whereby we are saying we're going to have x squared tan y squared plus 3 plus 3y, no, plus 3x. Yeah, sorry, y is, oh, I'm so sorry guys, I make y the subject because we said y is not the subject with implicit. So I have x squared, I'm so sorry, tan y squared plus 3x squared is equals to 27. So this is our implicit function, right? This is our implicit function. So with this one, we're doing the same thing again. D dx of x squared tan y squared plus 3x squared is equals to d dx of 27, isn't it? So now we find the first derivative of both sides, and then when we're looking at this side, we have, first of all, we have this term and this term, right? So let's start with the first term. Dx of the first term, which is x squared tan y squared, isn't it? So what's the first derivative of this one? The first derivative of this one, of course, when you're looking at this function, we have the x, we have x and the y function, right? So we have 1, 2 functions that are multiplying each other. So automatically you're going to use what? We're going to use the product rule. So looking at this one, the product rule is going to be what? I'm going to leave what? I'm going to leave tan y squared, and then I'm going to differentiate what? X squared, which is 2x, plus I'm going to leave x squared and differentiate what? Tan y squared. And remember, when you're differentiating this one, first of all, we differentiate what is inside the trigonometric function. Remember, we're using the chain rule within the trigonometric function. We're differentiating what is within the trigonometric function, which is 2y. And when you're looking at what is inside the trigonometric function, it's a y variable. So we are going to say dy dx, right? Times, of course, the derivative of tan is what? It's x squared y squared, right? And then this is it, isn't it? So now this is the first derivative of x squared tan y squared. We use the product rule by we first find the first derivative of what? Of x squared, which is 2x, right? We left tan y squared, and then plus we leave x squared. We found the first derivative of tan y squared, and then the first derivative of tan y squared is going to be what? It's going to be 2y times dy dx sec squared y squared. Why? Because this is, we have tan y squared, right? So when you're finding the first derivative of this one, we find the first derivative of what is inside, which is going to be 2y, right? Multiplied by, this is a variable of y, of course, it's going to be dy dx times what? Times the first derivative of tan y squared, which is going to be sec squared y squared, right? So we have to go back to trigonometric functions, guys. Where you have to know that d dx of tan x is going to be what? Sec squared x. You have to know this rule. That's what we applied here. So these concepts are building on top of each other. So if you don't know the basics, you just have to go back to the basics. We spoke about this last time. So now, remember we had our initial function. This was our initial function, isn't it? This is 27, not 2.7. This is 27. So we are finding the first derivative of this part and this first derivative of this part. So now d dx of these two terms, right, is equal to d dx of 27, isn't it? So now we have found the first derivative of the first term, which is what? The first derivative of the first term is the first derivative of the first term, d dx of the first term. We said we found it here, right? So this just simplified. This is going to be 2x tan y squared plus 2x squared y sec squared y squared dy dx, right? So it's what? 2x squared y sec squared y squared dy dx. We just simplified this part. We just simplified this part to this part, isn't it? So now we found we have to continue again dx. Now we are finding the first derivative of the second term, which is 3x squared. This is going to be what? 6x again, right? So therefore, the first derivative of this entire function as it is, and the first derivative, of course, of 27 is 0. We know that. So the first derivative of this entire function is going to be what? Is going to be, therefore, this one is going to be what? 2x tan y squared plus 2xy sec squared y squared dy dx is equals to, the first derivative of 27 is what? Is 0, isn't it? Because 27 is a constant again. So you just make dy dx the subject of the formula from here. Therefore, dy dx is equals to what? Minus 2x tan y squared all over 2xy sec squared y squared, isn't it? So just to simplify this, 2x will cancel, 2x will divide each other from both sides, so that you're left with dy dx is equals to tan y squared over y sec squared y squared. So this is our implicit derivative of this function here. We get dy dx is equals to tan y squared over y sec squared y squared. I'm going to try to find videos that can explain this concept a little bit better, and then I'm going to post them on the group so that you guys can practice. But next time, Monday, we are going to start from the implicit derivative. I'm just going to do one more equation, and then one more equation, and then I will take, if you guys have any queries, we're going to address them for the first 30 minutes, and then we're going to move on to parametric derivatives and so forth. Thank you.